Hi, everyone. My name is Gargi, and I'm going to be talking about Syscalls for Rustaceans.
Hi, can I turn your mic on?
Oh, sorry. I forgot that. Now I don't need to speak up anymore. Yeah. Yeah. And if you want to follow the slides along, here's the link. And yeah, let's get started. So before I even begin to talk about system calls, I want to talk about what it means to be a systems programming language. So it's a term you hear a lot in context with Rust, like Rust is a new systems programming language. But what makes a programming language a systems programming language, and what makes C and C++ and Rust good candidates for systems programming languages versus Python and Perl and not so good candidates for systems programming languages. So I want to take us through a tour of history and talk about the evolution of systems programming languages. So the three themes that I will be sticking to in this talk will be, what does it mean to be a systems programming language? What makes Rust a good candidate for a systems programming language? And third is learn about system calls and writing your first system program in Rust if you haven't written it already, and to empower people to write more systems programs in Rust. My research tells me that the first time the systems program term was coined was in 1970s. So this was the era where we were improving on assembly. And the author of this paper called Systems Programming Language defined a system program as an integrated set of subprograms exceeding some threshold of size of complexity. So some examples of such systems would be like simulators or time-sharing systems or information management systems. And then the author goes on to define what system program is. So a system program is likely to be used to support other software programs. This system program can be an application in itself, or it can be used to support something else. For example, the operating system is written in like some systems programming language like C. So if you want to read from or write to files on disk, the operating system would provide you the functionality to do this. It makes sure you have, it makes sure you have programs to access permissions, to handle multiple files, of accessing files and loading blocks into memory, and so on. And it is likely to be continuously evolving. So it is in contrast with the systems of 1970s, where you had one-shot solution to a single application rather than continuously evolving systems. The key idea in this paper is descriptive, so defining a system. But the key idea in this paper is prescriptive, so separating the language at the time, assembly, from Fortran, which was more higher level. A language which can be used without undue concern for bit twiddling, which can be used to design and write more systems without unnecessary overhead on our resources. And the last paper from 1970s was the paper called Systems Programming by Donovan. So the first time we had computers, we dealt with them using on and off switches. And then we wanted to do more complicated things, like if I have y, which is 50, and I want to calculate x, which is 30 into y, how do I do that? So present-day programs cannot understand these without the aid of systems programs like microprocessors and compilers and assemblers, and et cetera. So to make computers better adapted to the needs of the user, we need systems program, is what the paper said in 1972. And then in the 70s and 80s, most researchers saw systems programming languages in contrast with assembly programming. There were simply no good tools to build systems. However, in the mid-90s, it was the rise of dynamically typed scripting languages. So bash languages like Perl, Python, Ruby gained steam and made their way through the mainstream. And systems programming languages were designed to build more primitive computer elements, versus scripting languages were designed for gluing. So you can separate scripting languages and systems languages technically you can separate them on the axis of type safety, versus if you were to separate them on the axis on the basis of design, you can say that systems programming languages are designed to build more complicated software, versus scripting languages are designed to glue those components together. And so in 2010, around that time, the boundaries blurred. So massive resources were put into Java, building just-in-time compilers for JavaScript, like V8 or Python SciPy, and their performance is not better, but if not better, almost as competitive to C and C++. And Dropbox was able to build its large and scalable system on just Python. JavaScript is used to render real-time UIs in billions of web pages, and there was gradual typing in JavaScript, and Python, which enables people to transition from prototype to production code, and large-scale distributed systems languages like Go and Go, etc. Go, etc. put in resources so that garbage collector languages also performed well. Which all of this leads us to what does it mean to be a systems programming language today? So languages in the category of C and C++ and Rust and D are distinguished in the terms of the level of abstraction they provide you from the machine. So the languages expose the details of underlying hardware, like memory allocation, layout, etc. So when you have an efficiency problem, is it in your power to eliminate the bottleneck? So the wonderful part about these languages is that they provide you the confidence. So if you have a statically typed language and you say, this language gives me the confidence that if I'm adding these two integers, I'm going to get a result which is an integer. The same way, these languages give you the confidence that if I'm executing this instruction in a machine, then it will work exactly as I want it to. So lower-level programmers should seek to understand how the system design could be adapted to the reality of modern-day hardware. And something Rust does really well is that it takes the ideas of like functional programming and lower-level problems like futures and type safety, of course, and uses them to make the language better. And we should also consider the added benefits of using Rust, which is which are enabled by Rust type system, which is static information flow control and safe traversal of pointerless data structures and software fault isolation. And with that, with the history of systems programming languages and where we stand today, I want to jump into the next part of this talk, which is, before that, you can throw everything aside out of the window. And systems programming is when you spend more time looking at math pages than reading the internet. So with that, I want to jump on to the next part of my talk, which is writing our own STRACE. So with this, I hope to empower you to write your own STRACE or even more complicated systems programs. So let's say you have a user program and user process, and you want to do something that seems as trivial as reading from a file, but your operating system has the necessary privileges to read the file. It has the file descriptor, and it has the location of the file, and you want to read this file, but you have to talk to the operating system to do that. So who are you going to call? System calls. So you can think of system calls as an interface between your operating system and user program, or you can think of as an API that is given by the operating system to you for you to use. And there's like around 330 system calls on Linux. Some of them are very esoteric, and some of them are very common. So some of the common ones for like file access are create, read, write, open, and close. So I included create here because when Ken Thompson was asked if he had any regrets about Unix, he said, I wish I had named it CREATE and not create. And which is also the system call is obsolete now because of open, but I included it for that joke. And the more system calls. So for like process control, if you want to wait for a process, you can use wait or wait PID. If you want to kill a process, you would use kill. If you want to spawn another process, you would use fork. And for network access, you have socket when you want to create a socket, get sock OBD when you want to set or get the options on a socket, or when you want to listen to a socket, you would use listen. So what happens when a system call occurs? Let's say we want to read from a file. So the user program would push the number of bytes it wants to read, push the buffer, which is the address of where it wants the result of the read to be stored, and the file descriptor into registers, and it will call read. And then it goes to a library procedure, which will put the code for the system call in a register. So each system call has a number associated with it. For example, read is 0, open is 2, and so on. So you put the code in the register, and you send a trap to the kernel. And then now there's a context switch, and you go to the kernel. The kernel will go and look into the register for So when you send a trap with a number. So that number is the number of the system call. And in the operating system, there's an array where like the kernel goes, oh, you sent 0, and 0 means read. So I'll go and now look into the registers of like what file I have to read and where I have to store the result of the read. And once the kernel does that, it switches. There's another context switch back to the library procedure, and finally to the user program. So one thing to note is that system calls are fairly expensive. You have 2 context switches involved. So making a system call is you have a register where you would have the file descriptor stored, a register where you have the buffer stored, and the register with the count of bytes that are to be read or read, for example. So you set up a register with a system call number and parameters. You send a trap to the kernel, and you get the results stored in the register. But the good thing is we don't have to do it. We don't have to do any of this because Unix provides us with a library called libc, which is a C library. And the problem that most Rust programmers have with this library is that it has it has arcane types. So it gives you white pointers, a lot of white pointers that you'd have to use. But it's still an API, so that's cool. So now that we have an idea of what happens when a syscall occurs and how do you make a syscall, I want to jump onto what is STRACE. So STRACE is a Linux debugging utility which allows you to debug closed source programs. For example, if you have, and it allows you to identify bottlenecks in the program. So we already know that system calls are expensive. So if you have a program and you want to optimize it for its performance, and you see that it's making more open calls than you thought it would, you can go and optimize. The STRACE will tell you how many open system calls your program is making, and you can go and optimize for that. And it's also invaluable when you have closed source program. You can't just go and attach GDB and say, oh, please stop at line 12, because you don't know what's at line 12. So in that case, if you have a closed source program which you thought is not working like you wished it would, and you go and see the STRACE for it, and it's opening X instead of opening Y, STRACE will tell you that. So if I have a very simple program which says, hello, RustConf, and I see the STRACE output for it, I'm not sure if it's visible, but I will still say what it is. So it first has an exec system call, which is executing my script, and then it has a break, an access, an mmap, and so on, and it lists all the system calls that are made in that order. And if I have STRACE-C, which will tell me the count of all the system calls that were made. So I have 11 system calls to read, and 9 to open, and so on. And it will tell me all the system calls that were made, which is pretty handy. So that's now is the last part of my talk, which is we will write our own STRACE. So we need 3 things to write our own STRACE. One is we need to know how to observe another process, which is an important part because we want to find out how many system calls this other process is making. Second is how to trap a system call. Once we know that we have a process, how do we know that it's making a system call? And the third is once we know that system call is being made, that's very cool. But now we want to look at the registers to see what's happening, or like what system call was made, because the register stores the value of the system call. So how do we observe another process? Well, system calls to the rescue again. ptrace. So ptrace is not a POSIX system call, which means it has different behaviors on different operating systems. But for Linux, we have ptrace. So you have a tracer and a tracee, and what ptrace allows you to do is observe and control the execution of this other process, which is very shady. Because you can go and change the registers of this other process and do malicious things. But the good thing is that if you want to observe another process, this other process has to give you explicit permission that, yes, I want to be traced. And the second is, if you want to trace this other process, you need to be in the parent namespace of this process. So the first line of this code is the process giving me explicit permission to trace it. And the second is me spawning this process so that I can be in the parent namespace of the process. And the next thing we care about is how to trap a system call. So ptrace to the rescue again. So every time the process that we are tracing makes a system call, a sig trap is sent to the tracer, and then execution stops. So you can go and check the register if you want to, and you wait on this process. So you will stop every time a sig trap is sent. So ptrace to the rescue again. It has a flag called ptrace system call, which means that every time a system call is called, a sig trap will be a sig trap would be sent, and you can stop and inspect the registers or arguments to the system call if you wish to. And then you can start so this will happen in a loop, so you can resume your process again, and then the next time a system call happens, you stop again, and you can inspect the arguments again, and so on. And then the last is how to fetch register values, which is, again, ptrace. It's amazing, I know. So ptrace has a flag called ptrace_getRegisters, which will get you all the registers. But once you get all the registers, you have to know which register stores which value. So I found out through Googling that the array X register stores the value of the stores the number of the system call. So you can use that to find out what system call was made. And yeah, I have a demo. Oops. So I have a simple program called, can people see it? Cool. I have a very simple program called hello.rustconf. And in this, and I have another Rust file which stores all the 332 system call names. So 0 is read, and then 1 is write, and 2 is open. I should make a crate or something. I don't know. Yeah. And then in this main program, I have like a function called getRegisters, which will get me the registers. And then I allow the child allows the parent to trace it, and I spawn the process. And in this loop, I will get the registers and map the system call names and insert in a map. And if I want to run STRACE on hello, oops, sorry. Yeah, and then it says hello RustConf, and it will tell me that close was called 9 times, and fstat was called 7 times, and read was called 11 times, which is pretty neat. Yeah, so in conclusion, I want to say, oops, sorry. In conclusion, I want to say that Rust is very empowering, and it's so much cooler than C or C++ because because it follows the adage that if it compiles, it will work, which is not true for C or C++ at all. And if you were doing this, you would have to do memory allocation and other things which are hard and scary for new people. Yeah, so, and I would like to give a reminder that systems things are not hard at all if they are explained well and are made more accessible to more people. It's like, if you think about networking, it seems very hard because it has all these intimidating concepts, but then it's like the core concepts are like IP addresses and ports, etc. And once you understand them, you can learn a lot. Thank you so much. Also want to give a shout out to Arsha, Shalom, Haley, Taylor, Carrie, and Ruthio, Harris, Hasim, and Steven for helping me with this talk. And thank you so much.